Last time, we mentioned this relation between commutator, the vanish of the commutator between A and B operators, and the existence of a simultaneous eigenstate of A and B. And we know that these two are really sufficient and necessary conditions for each other. But we prove only partially, so today we will provide the remaining proof of the statement. In particular, this is what we missed. So suppose A and B operators commute, and can we find the simultaneous eigenstate of A and B? And last time we showed that if there's no degeneracy, if there are no degenerate states, and indeed we showed that if A and B commute, and we can really find a simultaneous eigenstate of A and B. So today we will finish this proof by considering a more complicated situation where we do have a degeneracy. So remember, definition of the degeneracy is that we have two orthogonal eigenfunctions which satisfy the eigenvalue equation of the same operator A with the same eigenvalue. So UA1 and UA2 are two independent orthogonal eigenfunctions. These are the eigenfunctions of the A operator, okay, with the same eigenvalue, but the UA1 and UA2 are different orthogonal eigenfunctions. So this is the definition of a degenerate states. So if you look at this two eigenvalue equation, you'll notice immediately that if you make a linear combinations of UA1 and UA2 with a prefactor alpha and beta, and you use the same operator A to act down to the linear superimposed, say, functions, and this linear combinations is some quantum state, right? Some wave function, and this wave function satisfies the eigenvalue equation for operator A because this simply just pull this alpha and beta coefficient out of this equation, and you use this eigenvalue equation for degenerate states. You can very easily see that the states, the new state or new wave function, which is made of the linear combinations of UA1, UA2. Remember, UA1 and UA2 are orthogonal degenerate eigenfunctions of A operator, but the linear combination of UA1 and UA2 is also an eigenfunction of A. This is very important message because this new wave function satisfies the eigenvalue equation for operator A, and therefore it is qualified to be an eigenfunction of A. So the conclusion is that any linear combinations of this degenerate eigenfunction is also an eigenstate of A. Okay, so we will take advantage of this result later, but let's look at this statement here, or the claim that we need to prove. Suppose A and B operators commute. Okay, so what is the consequence of this commuting operators A and B? Well, the consequence is that this B operator acting on UA, as we showed last time, is also eigenfunction of A, right? So the important conclusion from this line is that B acting on UA is also an eigenfunction of A. Because if you look at this red bracket right here, so B as an operator acting on any wave function or eigenfunction is also another wave function, right? And the red bracket is some wave function, and this some wave function satisfies the eigenvalue equation for operator A, and therefore this something is also an eigenfunction of A. You got that? So what are those possible eigenfunctions of A? Of course, the eigenfunctions of A could be UA1, UA2, or any linear combination of the two, right? As a result, you can very easily see that B acting on UA is an eigenfunction of A, and B acting on UA2 or UA1, both results are eigenfunction of A. But of course, UA1 and UA2 are different orthogonal degenerate eigenfunctions of A. As a result, you could consider this eigenstate of A in general a linear combinations of UA1, UA2 with all different coefficients, alpha, beta for the first line and alpha bar, beta bar for the second line. Because UA1 and UA2 are two different eigenfunctions, and when the B operator acts on this UA1, you get some linear combinations of UA1, UA2. But when it acts on the UA2, you get another linear combinations of UA1, UA2 with a different coefficient. So let me summarize these two relations right here. So you get these two linear equations, linear coupled equations, and you can use your knowledge in vector analysis or matrix eigenvalues of matrix. You could very easily see that this is nothing but what? B acting on this UA1 and UA2 right here, beta, alpha bar, beta bar, UA1, UA2. Okay, so you may be able to write down this two coupled linear equation in terms of the matrix form, and so then we could really see the eigenvalues of this matrix formed by these coefficients, and we try to diagonalize this 2 by 2 coefficient matrix and find the eigenvalues and eigenstates of this 2 by 2 matrix, and the eigenvalues could be easily assumed to be, say, some different numbers b1, b2, and the eigenstates corresponds to the linear combinations of UA1, UA2, which diagonalize this relation, which decouple these two relations. So in a new basis, which is formed by the linear combinations of UA1, UA2, and this basis is nothing but the eigenvector of this 2 by 2 matrix. Right? So in this basis, we could rewrite this eigenvalue equations, coupled eigenvalue equations, in an independent way. So the B operator acting on VA1 gives you just B1 times VA1, and so for the VA2, so the equation for VA1 is decoupled from the equation for VA2, right? So the VA1 and VA2 are the eigenvectors of this 2 by 2 matrix formed by these coefficients, and so it is this VA1 and VA2 that we need. So we do not simply just take UA1, UA2 and say that these are the simultaneous eigenstate. No, they are not, because you can see that any linear combinations of UA1, UA2 is also eigenstate of A, and you can take two different linear combinations, and they may not necessarily be independent. Okay, so we need independent orthogonal eigenfunctions which serve as the simultaneous eigenstate. But what are those orthogonal independent eigenfunctions? Well, it is exactly VA1 and VA2, because these two are the orthogonal eigenfunctions of this eigenvalue equations, and they are independent. They are linearly independent, and they are eigenstates of the B operator. So this is exactly what we want. As a result, we simply just call this VA1, VAB1, and VA2 as VAB2, because this VAB1 and VAB2 are exactly the simultaneous eigenstate that we are looking for. So let me just summarize this result in terms of the eigenvalue equations for A and B operators acting on this VAB1 and VAB2. Remember, the eigenvalue for A operator is actually little a here, and for B operator is actually, say, B1 or B2. And we could also write down this eigenvalue equation for VAB2. So of course, this VAB1 and VAB2 are eigenfunctions of A operator because these just come from our earlier result that you make linear combinations of UA1 and UA2, and those eigenfunctions are also eigenstates of A operator. Okay? But what we do need is to separate this eigenstate of B operator in terms of a two decoupled orthogonal linearly independent eigenfunction, and which is precisely VAB1 and VAB2. So the final answer is that we do have a simultaneous eigenstates of A and B if A and B commute. And what are those simultaneous eigenstates? Well, these two are the simultaneous eigenstate, VAB1 and VAB2. Okay, so these two are indeed satisfying this eigenvalue equation for A and B operators at the same time, simultaneously, and they are orthogonal eigenstate, eigenfunctions. Okay, good. So that's the final proof. Okay, so a little bit complicated. We have to take advantage of this linear algebra and vector analysis and matrix product to argue that we do find orthogonal eigenfunctions which are simultaneous eigenstates of A and B if A and B operators commute. Okay, so now we finished the proof, and this is a very general, whether or not we have the general states, there's always true that whenever A and B operators commute, we can find simultaneous eigenstates of A and B, and vice versa. Suppose we have a simultaneous eigenstate of A and B, and these two operators must commute. So these two must go side by side. And this statement is really, really important in quantum mechanics, and we will use and apply this theorem, a statement, many, many times. Okay, and in the following, we'll talk about this simultaneous eigenstate of more than two operators, such as 3 operators and n operators, and so on, because we will need this information when we discuss angular momentum operators in hydrogen atoms and in general in quantum mechanical systems. So suppose we have more than 2 operators that are relevant in our quantum systems, and we should, of course, need to analyze the commutation relations of all these operators between them, between any 2 of them, and then whether we can find or we cannot find a simultaneous eigenstate. So let me just emphasize the importance of a simultaneous eigenstate. Suppose we have found the simultaneous eigenstates of A and B, and immediately this immediately tells you that A and B should commute, right? And the value of this commutator of A and B immediately tell you that there is no Heisenberg uncertainty relation, because you can see that delta A and delta B, when you make a product between these two, vanishes. And remember, it's delta A times delta B square greater than or equal to a quarter of what? Expression value of the I and B commutator square, right? Remember that. So when these 2 operators commute, we could for sure make measurements A and B quantities 100% accuracy at the same time. If not, then there must be uncertainty relations when we take the measurements with A and B operators. Okay, so whether we do or do not have Heisenberg uncertainty relations depends 100% whether these operators commute or not. Okay, so, and this is the heart of quantum mechanics. It's all about the commutation relations. simultaneous eigenstates and the Heisenberg uncertainty relations. So now all these three important ideas and concepts are linked together in this very important theorem right here. Okay, so let's take a short break. When we come back, we will generalize this theorem to more than two operators. Let's continue. So we proved this important theorem saying that this vanish of a commutator between A and B operators implies if and only if the existence of a simultaneous eigenstate of A and B. So now we generalize this idea to more than two operators, say three operators. Suppose we have this vanish of this commutator between any two operators of the three, such as the LZ, the z component of the angular momentum operator, which we will discuss when we talk about the hydrogen atoms in three-dimensional space. And as H is another operator, which is the Hamiltonian operator of a hydrogen atom, for example. And the magnitude square of this angular momentum operator, L squared, is the third operator called C. So there is operator A, operator B, and operator C. Okay, so you take any two of these three, and you find that the commutator between any two of the three vanishes. So LZ commutes with H, and L squared commutes with H, and LZ commutes with L squared. In other words, A and B commute, and B and C commute, and A and C commute. Right? So if we have such a wonderful relations, then we can immediately apply the theorem that we just proved. We say that since A and B commute, we have a simultaneous eigenstate of A and B. And since B and C commute, we have a simultaneous eigenstate of B and C. And since A and C commute, we have a simultaneous eigenstate of A and C. Okay? As a result, we have a common eigenfunction or eigenstates of all the three operators, A and B and B and C and C and A, right? So suppose this is a simultaneous eigenstate of all the three operators, and we call this WABC. Then we have the three decoupled eigenvalue equations, which exactly say this. When A operator acting on the simultaneous eigenstate W, you get eigenvalue A times the same eigenfunction. And likewise, when B applies the same state, you get another eigenvalue B. When C applies, you get another eigenvalue C. And little a, little b, and little c are different eigenvalues, but the WABC is the same eigenfunction. Okay? So now you can say that these three operators, A, B, and C, or the square of angular momentum, the z component angular momentum operator in the Hamiltonian, these three operators form so-called commuting set. Okay, so when we say that these three operators form commuting set, we must understand that if you take any two of them, okay, and they must commute. Okay? So, in other words, if we have a partial relations, not complete commuting relations, then we cannot, say that they form the commuting set. Suppose A and B commute, and B and C commute, but A and C do not commute. Then the maximum components in the commuting set is not three operators. It's only two, because we have commuting set of A and B and commuting set of B and C. That's it. Because A and C does not commute. So we cannot include all the three operators in this commuting set. Okay? So whatever these operators are classified in this commuting set, any two of these operators must commute. You cannot miss any commutation relations. All right? So this is called the maximize, the largest amount of commuting variables. It's called complete set of the commuting operators. Okay, so we will take advantage of such simultaneous eigenstates of 3 operators when we talk about the 3-dimensional hydrogen atom. So you could generalize this to any number of operators in this commuting set. Suppose I have this many operators A, B, C up to Z in this commuting set, and which we say that any 2 of these operators must commute, and we have a simultaneous eigenset of all these operators up to Z. And this is the largest amount of information that we could, in 100% accuracy simultaneously, okay, as I mentioned. So the eigenvalues, little a, little b, little c, up to little z, this set, eigenvalue set, is the largest of information we can have about the system with 100% accuracy and all at once. As I mentioned, when all the operators commute with one another, and we have a simultaneous eigenstate, right, of all the operators. So once the system is in this simultaneous eigenstate, and we cannot change this eigenstate by perturbing this away from this eigenstate, it will stay there forever. As a result, we have 100% accuracy when we take the measurement of all these different operators. And we could get this accurate information simultaneously or at once. So this is what I said. If they do commute, then we do not have the Heisenberg uncertainty relations. But on the other hand, so if we do not have this commuting set, or if there's another operator which does not belong to this commuting set, then we cannot have an accurate information on that measurement, provided that we are in the simultaneous eigenstate of this commuting set. So suppose there's another operator called Q, which does not belong to this commuting set. Then the measurement of Q will not give a sharp value. So when we take the measurement of this Q operator, it will not give us a sharp value, which means that we do have Heisenberg uncertainty. Okay, so this is the same statement. When we do have Heisenberg uncertainty relations, remember delta x times delta p is greater than or equal to 1/2 h bar, right? As a result, both delta x and delta p are non-zero. When the error bars are non-zero, of course, it is not sharp because it is broadened by this standard deviation, right? If you take the measurement of something and you find that this shows a very broad future with an error bar defined by delta x, and of course this kind of distribution is not a sharp distribution, and the value that you get from this measurement on Q is not sharp. It is a very broad distribution, and this broad distribution is a consequence of this Heisenberg uncertainty relation because delta x and delta p are non-zero. And why is that? Well, because Q does not belong to this commuting set. So that's the reason. Okay, so I guess this concept idea is really general and broad. You can generalize this to all the quantum mechanical operators. And let me just give you a well-known example which we discussed previously, which is it's a free particle in one-dimensional space. And there's no potential, just one free particle in one dimension. Okay, so we know very well that Now you have this Hamiltonian, which is made of only kinetic energy, right? And we have the eigenstate of Hamiltonian, which is also the eigenstate of a momentum operator. And the solution of this problem is what can be expressed in terms of e to the ikx or e to the minus ikx, or cosine and sine of kx. Remember that. Okay, so as a result, we have three operators: the Hamiltonian, the momentum operators, and the parity operators. And we say that we also show that this, both momentum and the parity operators are commuting with the Hamiltonian, right? However, the parity does not commute with momentum operators. So remember that. And we have already shown, indeed, the momentum operator does not commute with the parity operators in class. Remember that. But we do have these two commuting relations. Okay, so this is exactly what I said right here, that we have two sets of commuting operators. What are those? Well, we have h and momentum, and we have h and parity. However, we do not have the three. This does not exist. Why? Because the parity operator does not commute with momentum operator. Remember that. As a result, we have a simultaneous eigenstates of Hamiltonian and momentum, and we have a simultaneous eigenstate of Hamiltonian and a parity. Okay, so what is the first simultaneous eigenstate? Well, this is precisely this exponential of plus minus ikx, right? So what is the simultaneous eigenstate of the second commuting set? Well, this is precisely the cosine sine, right? Okay, so you already learned this. Okay, so now it's time to actually combine what we have learned, and we really reach a deeper understanding of this relationship between simultaneous eigenstate and Heisenberg Uncertainty relations and this commuting set. As a result, you see that we do not have a simultaneous eigenstates of P and parity. Okay, so, and this is already discussed in the class already, because you can see very clearly that e to the ikx, well, is actually a linear combination of cosine and sine. So it's a linear combination of these eigenfunctions of the parity operator. So it's not a pure eigenstate of a parity operator, right? So this is parity even, this is parity odd, and this is the reason why we have the arrow bar when we take the measurement. Okay, so if we are sitting in the eigenstate of the momentum operator, say e to the plus ikx, and we like to take the second measurement about the parity of the states, of course we have a 50% of chance that we see this is in the cosine kx state of the parity operator, another 50% percentage of the chance that we see that it is in the sine kx state of the parity operator. Okay, as a result, we do not have a accurate measurement of both operators at the same time. Okay, so likewise, you could think of this in an opposite way, that suppose we are staying this cosine even parity states initially, then we want to measure the momentum variables. The same problem arises because suppose we stay this in the cosine even parity state initially, then we take the second measurement, on this momentum variables. Again, we have a 50% of chance, another 50% of chance to get this, right moving particles with plus momentum, and another have a chance that we do find the particle go the opposite direction, minus k. So it's 50-50. As a result, if you take the 100 measurements, then maybe 50 measurements, you get plus k, another half you get minus k. So if you get 100% accurate result for this parity, this is 100% accuracy in the parity. Then for the second measurement of momentum, you get a 50-50, right? So in a similar way, if you're 100% sure that you're in this right moving particle states and you want to take the second measurement of parity, again, the second measurement gives you 50% of the chance that you get even odd parity state. So either way, okay, so you do not have a situation where you take two measurements and two measurements give you precisely 100% accuracy. It's not possible. The reason why it's not possible is because precisely these two operators do not commute. Is that clear? Okay, so this is a very simple example, which is application of this important general theorem, which relates the simultaneous eigenstate and the accuracy of the measurement or uncertainty of the measurements, and also this commuting set. Okay, so I think this is something that you have not thought about previously, and it is one of the core statements in quantum mechanics. It is the commutation relations, simultaneous eigenstates, and the measurement. Okay? So this is not mathematics, this is physics. Okay, so the example that I show here comes from this physical problem. You have a particle moving the one-dimensional line, and then here comes this relation. I suppose that all of you already learned something, or you seem to understanding something, but this will be the subject of a later discussions many times. So we will repeat such kind of statements future sections. Good. So let's take a short break. When we come back, we will change to the final topic of this chapter, which is the time dependence of this expression value and so-called equation motion in quantum mechanics and quantum to classical correspondence. 有吗？什么地方？那个 O and 问题。哪一个？那个是指导100%确认是确认成 A 跟 对。然后 O and 1是两个 measurement 同时得到100%精确的意思。对，这是两个 statement， 知道吗 ？O and 1是这两个 measurement 同时做。同时做不代表同时做，不是同时的意思就是不管你是先这个再那个，或者是先那个再这个都一样，反正就是说，或者是你两个 measurement 就是一起做也是可以的。一起做不代表它都很精确被你找到，就是说你做了 A measurement 跟 B measurement， 它可以是精确，也可以是不精确的。这就我之前提到的这个概念，也许你们还没有完全领会哈，就是说量子力学的实验呢，它不是做一次测量就够了，它要做几次测量。所以我说同时得到的意思是在一次的测量里面，或者是应该说是假设是两个 operator， 就是说我先 A 再 B 或先 B 再 A 都算是这一次，我可以做100次这种两个 operator measurement， 对不对？等于说我做200个 measurement， 每一次就是 A、B、A、B、A、B 这样子，但是每一次得到结果会不会 A 的都会一样 ，B 都会一样吗？不一定啊。 如果 A 跟 B commute 的话，那你量10000次、无数多次，结果都是一样的。A 的结果都是一样 ，B 的结果也都是一样。A 跟 B 同时做，同时得到一样的结果，同一次做的意思就是，如果 A 跟 B 不 commute 的话，那你第一次对 A 做可能是这个答案，第一次对 B 做是那个答案 A1 跟 B1， 那第二次做 AB 的时候，可能就变 A2 跟 B2 了，第三次 A3 B3， 以此类推，做了100次可能是 A100 B1 B100， 那你做了不同次数的 measurement 对同一个 operator 来说，那它如果是得到一样的结果的话，那就是表示100%精确。如果你每一次做的结果都不一样的话，那就不是100%精确。对，如果 A1、A2、A3 都一样的话，那就是100%精确。这样你明白吗？就没有 error bar。什么叫精确？就是有没有 error bar， 有没有标准差。如果你每一次得到的结果都一样的话，哪来的标准差？就像是全班同学的成绩都是一样，都是100分，请问标准差是多少？0吗？不是吗？或全班都是59分，有没有标准差？没有标准差，你找哪一个同学来问你的分数多少，都是59分啊。没有标准差就表示100%精确，有标准差就表示不是100%精确。这样你明白了吗？量子力学它要讨论的其实是3种关系，一种是物理的存在，这个原子、电子的这些运动或者是这些交互作用；第二是数学 ，OK； 第三是实验 ，OK。这3个东西必须要在这个量子力学的架构里面同时要显现出来，所以他说的这些，就是说量子力学给你的这些方程式，它用数学的语言，用线性代数以及微分方程式，用矩阵，去来描述一个物质的真实的存在。那这些真实的存在呢，它是存在有某些不确定性，那需要靠很多次的测量，然后来知道它的统计分布。这个物质本身到底是什么东西，这是一个事情。那量子力学可以提供到什么样的说明是另外一个事情。那我们如何知道这个真实的物质存在是不是真的如同 Schrödinger equation 所描述呢？是要靠做实验去测量它。那每一次测量呢，根据量子力学都会，你可能得到不一样的结果或一样的结果。Okay, so mathematics, material and measurement or experiments. When you think about this quantum mechanical, say, equations or statements, you must simultaneously think about the 3 aspects. Okay, what is the reality? What is the real? What is the phenomena? How do I know this phenomena? What is the measurement? Okay, what is the equation telling us? Okay, very good question. So let's continue. So we have the knowledge of this relation between the simultaneous eigenstate and commuting operators. So let's just talk about time dependence of expression value of any quantum mechanical operator and its difference and similarities to the classical expression value or classical limit. So we know very well that any quantum particle satisfies the Schrödinger equation, but Schrödinger equation has 2 components. One is spatial dependence, another is time dependence. So we haven't discussed the time evolution of the quantum states in more details, but we should do it now. And we could take the expression value or the measurement of the A operators at any given time. Okay? So the T refers to time. Okay? It could be at initial time or any other given time. And this is, by definition, this integral like this. So integrate over the space, and inside the integrand you have this operator A in the middle of this psi star and psi, and both psi and psi star are the wave functions, which are functions of space and time. And so we will talk about this time evolution. So when we talk about the Schrodinger equation, the solutions actually evolve in time, right? So let's just take the time derivative of the expression value of A operators. Okay, and we will see this kind of expression value evolves in time. So how does it evolve in time? So we need to know the equation motion for this expression value of a quantum operator A. So let's just take the total time derivative of this right-hand side of the equation, and we'll get, right? So in principle, this operator A could also depend on time. By chain rule, when you take a total time derivative of this integral, you get three contributions. One is the partial time derivative of the A operators. Another two are the partial time derivative of this psi star and also psi, right? But you know this Schrodinger equation, right? What is the Schrodinger equation? Right, so this is a full, complete version of the Schrodinger equation, including space and time. So this IH bar partial psi partial t is given by the Hamiltonian operator acting on this psi wave function, right? So then you could rewrite this too. By using the Schrodinger equation. Right here, you could rewrite this partial time derivative wave function psi in terms of this Hamiltonian acting on psi. So let's do it. The first term is simply just the expression value of this partial A partial t, because this is another operator, right? So it's partial A partial t is some operator, right? And this operator B is just a partial A partial t. So by definition, this is the expression value of the partial A partial t, which is the first term. What about the second and third term? Well, this is given by, so I simply just use Schrodinger equation to rewrite this partial psi star partial t and partial psi partial t. And so this is given by this h acting on psi divided by IH bar here, and with a start, and the other one is similar. Right, so now let's use our knowledge of this Hermitian conjugate of this quantum operators. Copy the first term, and we pull out this factor I over H bar, A psi, because H and H dagger is the same. Okay, so this, when we take this Hermitian conjugate of this bracket, we should what? We should take the I to minus I right here. So with the inverse, this is I in the numerator right here over H bar, and this H phi star is given by phi star H dagger. Remember that, right? But since the Hamiltonian is actually the quantum mechanical operator for total energy, this Hamiltonian operator must be Hermitian operator. Remember, we mentioned that. Okay, so H dagger is the same as H. So that's why I just put it H here, because H dagger, is the same as H when you do this calculation. So the third term, you could very easily write down the result. Okay, so pay attention to this minus sign right here. The second term gives you plus I over H bar, but the third term is minus I over H bar, because this I appears in the denominator. And the reason why there is a minus sign difference is because the star, that's complex conjugation. So let's just combine this, the last two. So it is the HA minus AH, right? Okay, so you simply just combine these two, because the psi star on the left and psi on the right are the same in both terms, And then, you could simply just combine these two by combining this HA and AH in the middle. Good. But what is this? You tell me. What is this? Well, by definition, this is the commutator, H and A, right? Good. But the commutator of two operators is another operator. As we already mentioned, that if you apply the these operators in the product form and acting on any quantum states, and you can consider this product of all this A, B, and C is another some unknown operators, which I call this D. Okay, so why is that? Because, as I mentioned, all these quantum mechanical operators can be written in terms of the matrix, right? So all the three matrices, A, B, and C operators are just simply just n by n matrices. The product among A, B, C operators is also an operator because the product of the three n by n matrices is again another n by n matrix, right? Okay, so since it is written in terms of n by n matrix, it is again regarded as another quantum mechanical operator, which we don't know, simply just A times B times C. But you can see very well that this commutator between H and A is another operator, okay, which we call this O. So by definition, so in this second term right here involving this commutator is again some expression value of this operator O, which is the commutator of H and A. So you consider the commutator of H and A is another operator, and by definition, so this integral is the expression value of that operator. And what is that operator? This is the commutator, the expression value of the commutator of H and A. So let me just combine everything. So this total time derivative of any expression value at any given time is given by this expression value of the partial time derivative of that operator plus I over H bar times expression value of the H Hamiltonian and operator A. And this is called Heisenberg equation motion. So this is a similar but different way of finding this time evolution of expression value in quantum mechanics. Similar to classical Newtonian equation motion, remember Newtonian equation motion, we have F equals to ma, where a is the acceleration of this particle, which is the second time derivative of its position vector as function of time, right? So this is classical Newtonian equation motion. When we solve for this Newtonian equation motion, and we know the trajectory of any classical particles, right? For example, this kind of trajectory when you throw a stone, throw an object to the air, and you know that this classical object will actually fly, and then at some point and it will reach the maximum height, and then it will fall to the ground at a later time. So then we could actually monitor how this object flies, how the object moves as a function of time. So that's the classical equation motion, but quantum mechanically we cannot do it in a straightforward manner because we know the Heisenberg uncertainty relations affects all the measurements. So every time you take a measurement, you may find a different answer. However, if you take all this average over all these millions of measurements, and then you evolve this expression value of your measurement in time. Then this is an equation that controls such a time dependence of expression value. So this is the time dependence of your expression value of the operator A. So which satisfy this Heisenberg equation motion. So if this H and A commutes, then you have what? You have no motion at all for the expression value, but provided that this operator A does not explicitly depend on time. Okay, and this is often the case when we take measurements such as the Hamiltonian or total energy operator, or angular momentum operator, or spin angular momentum operators. So all these commonly appeared quantum mechanical operators are not explicitly time dependent, meaning this angular momentum operator does not depend on time explicitly. When we write down this angular momentum operator, it does not depend on time. Or Hamiltonian, and so on. Okay, so in most cases, at least in our class, we consider partial A, partial T to be 0. Okay, meaning that all the operators, when you write down this expression for these operators, it does not include time dependence there. Okay, but the average or the expression value does depend on time. And suppose this H and A commutes, and this A operator does not depend on time explicitly, then this expression value of the A operator is actually a stationary, meaning suppose partial A, partial T vanishes. Suppose Hamiltonian commutes with A, then from this Heisenberg equation motion, you immediately get that this dA average dt is 0, which means that this A expression value of A is actually constant of time. Meaning, whenever you measure this quantity and at any given time, it gives you the same this expression value. Okay, but oftentimes this Hamiltonian does not commute with its A operators. So then you could imagine that this expression value does evolve in time, and in a similar way but different interpretation from this classical equation motion. So we do not follow the particle literally in time, but what we follow is the average or expression value of a quantum mechanical operator. We monitor how this expression value evolves in time, which in some cases is related to this equation motion in classical limit. So this is something that we need to discuss further, right? So we will come back to this Heisenberg equation motion for a particular problem, such as harmonic oscillator problem and so on, and then we compare the solutions from the Heisenberg equation motion to the classical solution of this Newtonian equation motion. There are some relations. Okay, so let's discuss the Heisenberg equation motion as its connection to the classical limit. Okay, suppose that I could consider this operator A in this Heisenberg equation motion to be, say, position operators or momentum operators, and let's look at this consequence of these two different cases and see this classical correspondence. So in some sense, this results, if we take A operator to be X and P, something very similar to what we are familiar with when we study classical Newtonian equation motion. So let's just do it. Suppose operator A is given by this x operator. So let's just take the explicit value of the x operator, the time derivative of that x average, and by definition, so this is given by expectation value of this commutator between H Hamiltonian and this x operator. So remember, the Hamiltonian operator is given by the kinetic energy operator plus potential energy operator, right? So we consider a simple case where the potential operator is only depend on x. That's it, okay? So let's just compute the commutator. The commutator is the commutator between p squared over 2m plus the potential operator v and this x position operator. So let's just look at this simple commutation relation. So suppose we compute this v and x commutator, and we know that v is a function of the x. So suppose this is just a plus bx, for example. Then we know that x commutes with x, of course. The commutator between any two operators that depend on only one variable, such as the function of p or a function of the x, must vanish, because x and x commute. Why? That's really simple, because if you applied this to any quantum states, you'll get the same thing, because you cannot distinguish between these two x. So x is x. So this x is the same as that x. So it doesn't matter whether you exchange this x. You don't notice when you exchange this x. Do you notice that I secretly exchanged this 2x, but you don't know? Okay, so as a result, exchange these two operators are the same operators, and you really don't make such an exchange, because there's no difference between this 2x and that 2x. Okay? As a result, any two operators, if they are the same, they must commute. Okay? Using the same logic, so if you calculate this x squared commutator with x, the same thing. So any function of x commute with x, right? In the same way. For example, this x squared and x is actually x, which is x squared. I secretly exchange this 2x, but you don't know. In fact, I don't do any exchange at all, right? So it's the same thing. So x commutes with any operator as a function of the x, right? So likewise, p squared commutes with p. So immediately you get rid of one commutator, right? This v of x commutes with x, but so let me just write it down here. A plus b commutator with x is given by a plus b times x minus x times a plus b, which is the same as a x commutator plus commutator of b and x, right? Okay, so this commutator therefore could be decomposed in terms of two terms. One is the commutator between the kinetic energy operators and x, plus the commutator between potential energy operator and x, right? Simple algebra. Okay, but we know that this V operator is a potential operator. It's always a function of the x. As I mentioned, x commutes with all operators as a function of the x. So this commutator vanishes. So then we end up just this term. This is the commutator between the kinetic energy operators and x. So let's just do it. So you could show that the commutator between p squared and x is given by the sum of the two terms. One term is that the p operator p is left of this commutator between p and x. Another is px commutator is left of this p. So you know very well that xp commutation relation is actually minus what? Minus IH bar, right? Okay, so, right, or IH bar. Okay, so px is actually minus IH bar, sorry. So you got factor of 2 here, and then this is the final result. Okay, so we're almost done. Okay, so let's just look at this commutator. The final answer for this commutator is given by what? 2h bar times momentum operator, but divided by 2m times divided by I, right? Okay, so if you plug in this result back here and you simplify this, and this is the final answer. Okay, so the time derivative of this expression value of the x operator, the position operator, is given by the expression value of the momentum operator divided by m. But isn't that familiar to you? Doesn't it sound familiar to you? Well, what is the quantity in classical mechanics that is this? Momentum divided by the mass. What is this in your knowledge? Even in high school, you know that, right? Momentum in classical Newtonian mechanics is given by the mass times the velocity, right? Yes? So the momentum divided by mass in classical mechanics is precisely the velocity, right? Yes? Agree? Good. So then suppose I simply just remove this expression value. Suppose I remove this expression value. And just look at this classical version of this equation motion. This is nothing but this dx dt is given by momentum divided by mass, which is velocity. Right? So this is precisely this definition of a particle velocity in classical mechanics. The velocity is, is defined by the time derivative of the position vector. Okay, but in quantum mechanics, it is slightly different, but it makes a huge difference. Later, is that we put the expression value here, indicating that this x is not something that you know for sure. It's not this classical x vector that you could solve by solving the Newtonian equation of motion. No. We don't know where this particle is. We have to measure the position. We need to take 100 and 1,000 a million times the measurement for this x operator in a quantum mechanical problem, and we discuss time evolution of that expression value. We do not discuss the time dependence of the particle itself. What we do know is the time dependence of the expression value of an x operator in quantum mechanics. Right? But the final answer for that question bears striking similarity to this classical Newtonian definition of velocity, because we need to really match this two, because the velocity in any cases, either in quantum or in classical mechanics, should be defined as the momentum divided by the mass. But in quantum version, this is the expression value of the momentum operator divided by mass. Okay, which means that this is not the momentum measurement for each time, but we simply just take many measurements on these momentum operators, and we take the expression value of that measurements and we divide it by mass. Okay, so it's almost the same, but this kind of expression value makes a huge difference. So this is one limit that, or correspondence between this classical counterpart of the equation motion. So the second example is this momentum operators. When A operator is momentum operator, so what do we get? Well, again, let's just take this Heisenberg motion for this momentum operator. So as I mentioned, well, this is another limit of this commutator where we have the p squared and the p here in the commutator. So again, any function of p commutes with p. Okay, so this commutator vanishes. So you're left with only the commutator between v and p, right? So let's just compute this commutator. But to do so, we need to really operate this commutator onto any Schrödinger wave functions. Right? So the commutator between p and v is another operator, right? So this operator acting on psi gives rise to these two terms, right? So pv psi minus vp psi, right? But you know that when you write this momentum operator right here in the very left, the derivative partial x is actually applied to everything to its right, right? Whereas this p in the second term is actually in the middle, so it only applies to the function to its right. As a result, these two calculations give you different results. So let's just follow this definition. So this is given by, okay, so by chain rule, you can very easily summarize these two terms, and this is the final results, h bar of I dv dx times psi. So now you have this lesson, right? So if you apply this operator as a commutator acting on this psi, what you get is the spatial derivative, partial spatial derivative v times this h bar over I. As a result, this commutator has the effect that's h bar over I partial v partial x. Okay, so let's just plug in this results and back to this Heisenberg equation motion. So then we get what? We get minus dv dx average. So this h bar over I cancels the I over h bar, so and you pick up the minus sign here. So then this is the final result. So look at what it means. So let's just repeat this equation right here. Average p with the time derivative is given by minus partial v partial x expression value. Okay, so again, let's remove this expression value and see the classical corresponding equation motion for this. If I remove this expression value, so this is simply just dp dt is given by minus partial v partial x. Well, what is this? Well, if you remember your classical mechanics, this is precisely Newton's equation of motion, because this is this time rate of momentum, which is given by the force, right? This is the same as F equals ma. This is dp dt is actually m dv dt, right? In classical Newton's equation of motion, and dv dt is the time rate of velocity. The time rate of velocity is nothing but the acceleration, right? So this is ma. Okay, so on the left-hand side, dv dt is actually mass times acceleration. On the right-hand side, this is nothing but the force, because the force is given by the minus gradient of your potential. So the right-hand side of the equation here is nothing but the force in Newton's equation of motion. And if I simply just remove this bracket or this acceleration value, this is nothing but F equals ma. However, again, there's a huge difference right here. As I mentioned, in classical Newtonian mechanics, we can follow the particle and their momentum and velocity at any given time, but in quantum mechanics, we do not. What we follow is the time evolution of the expression value, not the momentum itself. Likewise, we do not simply just measure the force in quantum mechanics. What we do measure is the expression value of the partial v partial x. Maybe I think that's enough for today. So we have just one final remark which links this classical limit and the quantum version of the Heisenberg equation of motion and the difference between these two. So in what sense can we say that this Heisenberg equation of motion really is the same as the Newton's equation of motion? In what sense that they are not the same? Of course, in general, they are not the same, but the key point is whether I can remove this bracket, right? Whether I can remove the expression value. But in what sense that can we remove this expression value? And this condition will be the condition that this Heisenberg equation of motion reduces to classical Newtonian equation of motion. Okay, but here it's very clear that Heisenberg equation of motion in these two particular cases, when A is x or p, does look very similar and striking similar to the Newton's equation of motion. But there's just one subtlety here. So we cannot remove this expression value in quantum version, and we should put it here, and correspondingly we should understand this Heisenberg equation of motion in the context of quantum mechanics, not in the Newton's equation of motion, right? So in other words, Newton's equation of motion is the deterministic way of understanding the particle motion, meaning we can determine 100% at any given time the path of the particle motion, right? But in quantum mechanics, we do not. There's a Heisenberg equation of motion. Remember, this x and p do not commute. So we do have the error bar, standard deviation, and uncertainty principle, uncertainty relation between this measurement of x and p. As a result, we can only say this time dependence of the average quantity, not that quantity itself. Okay, so I guess that's enough for today. Let me summarize. So we have made important statements to link all this commutator and simultaneous eigenstate and the measurement, whether we have an uncertainty relation or not. And we also derive this Heisenberg equation of motion and discuss the relation between the quantum and the classical equation of motion. So next Monday we will just finish this final remark, and then we will move on to the chapter 6. And we will also probably maybe in the chapter 6 derive formally the Heisenberg equation of motion, this relation, remember, this delta A delta B greater than or equal to this quarter of this I commutator AB squared. Okay, so we will derive this formally in the coming lectures. Okay, so that we know, the origin of this Heisenberg crystal motion. Right, so that's for today.